the title of this lecture is Lecture 1, Cloud Computing and Big Data Introduction. So it's really giving you a lot of links between the different lectures that we will have in the course. It will be not as separate as in the prologue. In the prologue, we also covered lots of the material of the course, but mostly from 10,000 feet perspective. Here we already go several times a little bit more deeper, but of course we'll then link to necessarily lectures in the future in the course. But before we go into the material of the lecture of today, let us just review what we had the last time. And the last time was really a practical introduction about Python, about Jupyter. And the reasoning is that many data science applications today, whether it's in data mining, whether it's in applied statistics or machine learning, in one form or another, they all do this new term called data science, where they really have lots of computing needs, big data, so to speak, to process, and use perhaps high performance computing to do so, or even cloud computing resources to do data science, to do data analysis. Now, sometimes high performance computing can be also within the cloud. We will see that basically through several lectures in this course, where basically the HPC machine is within the cloud, and the cloud makes it easy accessible and really makes it more smooth, had a commercial market system around it, a business plan, the credit card swipe we will talk about to get access to cloud computing resources. And if you look today, really in all the major cloud services that I would say in the moment are really the three that you see there, the AWS, the Amazon Web Services. This will play a big role in the course already today. The Microsoft Azure, this is a cloud from Microsoft, which is also part of your first assignment. And then the Google Cloud has an extraordinary amount of services, features, and functionality that is also, of course, very much leading in the market. So all of these three have cutting-edge technologies underneath, which we also will explore when we see a little bit more inside the data center later. But the last time we really talked about this kind of aspects that if you want to access these clouds, then you need languages, programming languages, which are very popular in data science, which is Python. By far nowadays. In former times there have been R, and you will find still that of course there are R services, for instance, for statistics. You will find MATLAB instances for more applied mathematics. You will find a lot of older tools, I would say. And all of the tools which are in Python have really now got a lot of momentum in the data science community, and even also in the simulation sciences community that is more towards physics. Although in these areas where numerical laws and numerical methods based on known physical laws exist, they are traditionally more on Fortran and C. We see that data science really is Python oriented. And now we had a very practical idea last time and think like, okay, when we want to use this cloud, what's the difference? So how I do it, how I do a remote cloud access. It should be simple. I don't want to be having, installing lots of things. Perhaps a browser would be good. And we found that the Jupyter toolset is just perfect for this. So when we have a given problem that we have seen here, the number recognition, handwritten number recognition that we want to do in subsequent lectures, perhaps with deep learning networks, we have to do some pre-processing of the data. We have to understand the data first. Some data preparation is necessary. So we want to use Python for this, and we don't want to use it on our local laptop. Admittedly, the MNIST, what this character recognition is called, is rather small data. And this is, of course, rooted in the fact that we have 60 participants in the course. And if everybody is working with extremely hell a lot of data, then we are in trouble. But still, the same idea, the same way how we approach these systems now could be also done with real big data, of course. Then we talked a little about then how Jupyter works, how Python within Jupyter works. There are these cells, which are kind of very important. You get these numbers that you see there on the right-hand side, where people get numbers, what they executed, in which order. We talked a little bit about it, that the order is a little bit important. So also when you do your assignment, don't hop around too much. Rather think about restarting and clear your output for the kernel and then start from the beginning. Also, you have seen that involving libraries like Keras, involving libraries like TensorFlow, that if you remember in the prologue, played a huge role for deep learning these days. These are things tightly integrated into these frameworks. It's very easy to integrate them. As you see there, we integrate as just keras, the data set, and in subsequent lectures, we will also then use keras on top of TensorFlow with a very nice Python code, which is actually not really large. So in general, the data science code will be relatively straightforward and not like, let's say, a typical software engineering program that you maybe know from Java and Matthias Bog courses, where there are lots of sub-functions, lots of procedures, and different, let's say, classes and inheritance and so forth. Data science is much more straightforward, working on the data, but usually having several steps, including data preparation, data analysis, and then data evaluation. And we go in more details also in the next lectures. So having talked about this from the last time, let us now dive a little bit into what we want to have news today. And this lecture is meant as a kind of overview and looking back where cloud computing really comes from and how it really affected the movement of big data, and how essentially then big data in turn was really a hype that enabled new innovation really with deep learning, new innovation in machine learning models, which is quite interesting. And we will explore a little bit that cloud computing has a long history. It started with parallel and distributed computing in the past. We had lots of technology advances on the way that enabled parallel computing. Using systems for multiple users is one way to think parallel computing, but of course parallel computing is meant here that one instance of a program can also run on multi-core CPUs, use the advantage of GPUs, as many core GPUs we will talk about today, and then really what kind of different as-a-service approaches came along. And each of these as-a-services is today really popular. There's not a really straight line between them, they're kind of overlapping, but there's some, let's say, terminologies we will clarify in the first part of the lecture. Then the second part will be really more about big data, which is tightly intertwined now with cloud computing, with high performance computing, because usually you need big data in order to have deep learning done. You need high performance computing or cloud computing resources, something which really can deal with big data, because usually you have key challenges on the way. We will review not only disk capacity, also the kind of way how memory works on larger systems. This all plays somehow in the role of how we store memory and data and storages and all of this as a kind of ecosystem in a sort of hierarchical fashion. And this is, of course, an important aspect. So we will review more what cloud storages can offer, and we'll link then, of course, here now to different course lectures that we will face. We will also see then that the matter of fact of big data will be that you cannot ship it around very much. Even if you have good wide area networks today and the network bandwidth is increasing, we still have the need for distributed programming models, and thinking about that maybe the data should be just more or less be there where the data is and just shipping around the tasks. So we will look shortly around things like MapReduce, Apache Spark, these models that have enabled distributed programming. And then we'll talk at the end of the lecture a little bit what it enables in terms of machine learning, before we then with lecture 2 and 3 really practically more and more go into this topic. Okay, so fasten your seatbelt. Let's go a little bit into the history and to the foundations of cloud computing. So this is really, if you think about what it's from 10,000 feet, nothing really special in terms of computer science. You would say you always need some hardware. You would always have some software running on it. And the software usually have input-output data, so the storage might be valuable. And of course, now the internet cloud enabled us really to have networks, to have really fast networks to interconnect. And what then came along were service-oriented platforms, services-oriented architectures, first with SOAP, then more these days with REST services, where you really can offer within the internet several services. Underneath are resources which are virtualized. And we will talk about this really by far more in lecture 4. So I keep it like this here, that of course the virtualization in these data centers played a very huge role in the cloud systems that we have today. but also the service-oriented environments that are based on top of it for multiple users enabled really that you can, let's say, charge for services, that you can offer paid services where then users can have, so to speak, requests once they swipe their credit card, or they have a subscription model based on some way or another. They can use the services which are not locally on the laptop, but somewhere in the internet cloud. And this somewhere is really loaded, because you will see the more we go into real cloud systems, the AWS, the Microsoft Azure, or even Google Cloud, you will see that the concrete HTTP URI is getting less and less important. Also, you see already when you do your first assignment, you're essentially within the Microsoft Azure cloud, but you have no idea where it exactly runs. You could say something like East Coast maybe, or West Coast, or somewhere in Europe when you create an instance. But the point is here really to make it easier for people to use technologies which are traditionally more in HPC, high performance computing, which are, let's say, a little bit more complicated to use, a bit more low level, so to speak, than the cloud resources. And in this sense, the evolution towards cloud computing is really something which was driven ahead 30 years. If you look within a cloud, we still have the established computing paradigms. You would still have some farms with high throughput computing, where each of the different, let's say, cores are not really tightly intertwined, not tightly interconnected. This is really for throughput jobs that don't need to communicate a lot between each other. And then you have some of them which have, let's say, high performance computing resources to some degree. Of course, not directly to the exascale degree, what you can find in clouds today, but rather moderate sized clusters, which actually offers, for example, a moderate amount of GPUs that you can use. And this is really fueling the cloud still today. It's not that there's a complete new technology inside. It's just that this is rather hidden from users inside the cloud, inside different services which are running on these systems, in order to basically have a service portfolio that people can use, that people can charge for, and to really enable also to some certain extent the porting between different cloud vendors. So in a sense, you see that the foundations for cloud computing have been there since many, many years. And if you want to have, again, a comparison between high performance computing and high throughput computing that always existed basically within the history of computer science, you basically have this differentiation that you really look on the network interconnect. When the network interconnect is just a little bit of Ethernet, then you speak rather of a loosely coupled cluster of a HTZ resource. But if you have a high performance computing machine, then the interconnect might be something like InfiniBand, very dedicated interconnection protocols, which are inherent very insecure, because you're still within one machine. So there's no point of making it secure. And that's why you can achieve extraordinary speed between using all of these different cores. Of course, now in the future, as in the last, let's say 10 years, the CPUs and cores were now augmented with GPUs, but the key principle here between high performance computing and high throughput computing remains. When you now look over evolution over these systems over time, you really had the two ways of handling this. We had these HTC systems, which were more about file sharing, distribution, P2P networks, where it doesn't really matter that you have things not really interconnected very much. They could run in a very, let's say, coarse-grained, geographically distributed fashion. Then on the other side, we had really the HPC systems with very high speed performance, extremely costly, because the network interconnect is what really makes a HPC system so multi-million in cost, right? And so this is really centralized. It's a big system standing somewhere, and there were clusters, multi-purpose processors. There was a lot of movement by basically physical simulations based on known physical laws, numerical methods that really bring this ahead. And of course, I will talk about HPC systems in the other course much more, in the complementary high performance computing course coming next year again. But here we take it a bit more on the cloud, which one came later essentially, while there was a strong movement of bringing those worlds together. In activities called the computational and data grids, where really the idea was, let's connect all of the different resources we have, and even telescopes, because they're unique in science, or a certain different other technology, a tomograph machine, an MRI, hospitals with data together with the analysts. So having something called the internet, but with much more interesting resources like supercomputers, like, let's say, moderate scale computing, data silos, and so forth. This was rather successful in activities we have done, for instance, at CERN. We found the Higgs boson, as you know, and the Higgs boson would be not possible in physics to be found without grid computing. There is also a statement that you can find and also will be later on in one of the lectures. And one of the software elements we were creating was actually part of it. And lots of these elements then, from actually distributing the work across the globe, really with the internet, was then fueling the idea of really doing this internet cloud systems. I mean, these were times where Google was better, right? Someone knows that still? Right, where the Google search machine had a big beta on it. And now Google has unlimited amount of services, I would even say. They can deliver WLAN in any part of the world in a couple of days. No government today is able to do this. So you see that there was tremendous innovation along the line, and there would be basically the three ingredients which in one form or another are a little bit related to the big data and to the cloud movement that we have today. The one is really the service-oriented architecture, away from really program-oriented things like C can only work with C and then nothing more, but you can call from a C client, then a Java service and things like that. A whole movement with Web 2.0. SOAP was a very popular protocol initially. Then this is more transformed these days into the representational state transfer called REST. And REST services are all along. On the other hand, we see with big data that everything gets more or less an IP address. Everything has a sensor, your washing machine, whatever you go. Chances are in the future you have, every machine has sensors. And if not, it has some RFID chips that do something and measure and deliver data. And this Internet of Things, as it is called, is something like everything has an IP address in the world, from bus station to track the situation of the buses right now and the bus basically going through the town, up to really coffee machines and your fridge that can actually maybe order automatically depending on the sensors inside it and see what is best known and best needed right now. So you see essentially a long history, really 30 years. And if you look what this shapes everyday life today, that's just incredible. You can basically hardly say that our life would be anywhere near like today if you don't have cloud computing. And even if you think you don't use cloud computing, chances are, for instance, with Gradescope, right, you indirectly use the Amazon Web Services. So they are underneath the hood. And things like that. So we have the Google Cloud, very famous. Of course, the Google Docs, many people use. Then the Amazon Web Services, they fueling with their storage S3 systems, a lot of cloud systems, games we will see, apps, and so forth. I talk later about Microsoft Azure a lot. Facebook, I mean, everybody knows Facebook, a different type of cloud system, of course, an online social networking site. We will talk about this also in the second part. Salesforce, Rackspace, I cannot go to everyone. These are all different service models, different unique selling propositions that by large have now really enhanced the quality of our life today. Thinking about interconnect with another research group or with other business partners with Google Docs is as easy as it never was. Having engineers working together in the Uber cloud is very easy, and even scientists can share data in the EOSC, in the European Open Science Grid these days, and encouraged to do so. So you see, this cloud paradigm really has significant impact in all our lives. It actually also can be seen as one of the major driver why we can have apps today. Now a little bit on terminologies, just, we have a lecture in the university, so it's good to differentiate a little bit when we mean certain things and also things you find in the literature. In the past, we had lots of centralized computing. These were one big physical system, often high performance computing. Supercomputers, as they're also called, as really centralized centers, and also many data centers have been there in the past like that and are still today like this. However, there's some news that more open up, and in a way, the way how the accelerators, so GPGPUs, really influence the field had an impact of changing a lot of things within such a physical device to make it more modular. However, it's still a centralized computing system and very well interconnected with a network federation. As we here have an example in the DEEP project from a modular supercomputer, for instance, but still it's a centralized computing entity. So it's nothing like really the clouds we will talk about when we then think about the different data center strategies in lecture 4, for example. However, there's a certain approach called parallel computing, where you use different processors at the same time, either tightly coupled using shared memory processes, using loosely coupled when more distributed message passing is on the way. You see that a little bit on the right below there, that different processors work together on big data or on different data items. They share lots of messages between themselves, not only on the data, also on instructions. And that's what we mean as parallel computing. Also, parallel computing is much more taught in the complementary HPC course, where we really touch these programming languages. Here in the course, we keep it to Python, Jupyter to this level, but inherently are often parallel programs. And this is something really another takeaway message, how we can do things much more quicker than in the past, because some of the procedures can be very nicely parallelized. Another terminology that's really now is the essence of cloud computing is really distributed computing. So interconnect, as you see on the top right side, with the global grid, so to speak, which was there in the past, connecting almost everything, is a movement that continues with the Internet of Things. And part of this was then to have really this parallel computing, not within one machine, but really thinking about that parallel computing can be across different machines. So really thinking about that a cloud A, cloud B, cloud C together can do something. And even if they're all abstracted away for once, you see that on the bottom there, something somewhere very abstract, underneath are 3 concrete different cloud systems somewhere that maybe are geographically dispersed. So they're not in one site. Still, distributed computing enables you really to do parallel computing. And if you really are honest and look within HPC today, even within main HPC machine, we also talk sometimes about distributed systems because they're getting larger and larger. And you combine parts of distributed computing and parallel computing really to program these services today. This is a very important aspect, also what you see again and again coming in the course. And also to come back to the foundations of cloud computing to tell you that this is not really new as well. So this has been done in the BOINC that you see here. It's Berkeley Open Infrastructure for Network Computing, where there's SATI at home, there's Rosetta at home. There are different ways how you can contribute essentially your computing at home to a scientific endeavor. And here's one example from Rosetta at home, where you can actually basically contribute your spare cycles. If you don't use your computer, you install essentially a BOINC client and you contribute automatically by not being a COVID-19 scientist, of course, but you could use your free unused cycles to support the computing endeavor there. And this was a very similar system really coming in the past, and all the concepts around this that you use basically this distributed resources for computing helped also the cloud to get along and to get more stable. So the first BOINC middleware tools are really those that also inspired the initials of cloud computing. What cloud computing then really added was getting from science and engineering more towards the commercial world. So in BOINC, at these times, nobody was really thinking making money out of this. This was clear it is a scientific endeavor. We want to have, astronomy. We have basically medical aspects. Rosetta at home was now specifically here targeting COVID-19. So these are all different endeavors, but the clouds really then added the kind of credit card swipe to it, right? And here's a very popular one, which is a modern infrastructure as a service example. Of course, also this just as a first glance of a typical cloud provider. We will have much more of it in lecture 8 when we talk about the AWS much more. Here you see essentially one of the key services, an elastic compute cloud that you can actually buy And you can steer. Do you want to have many core GPUs? You want to have multi-core CPUs? Doesn't mean anything to you. I will explain in a moment what that is, the differences between them. But essentially, you can scale them up and down. So usually businesses have a moderate number of computing to do. Suddenly around Christmas, they have to do lots of different things. So taxes are coming end of the year. The Christmas shopping makes a peak in basically analyzing data. So you see usually that the demand is a little bit scalable, so that you have to grow and suddenly decrease the load. We will also talk about this in the data scientist much more, why we have to scale up, scale down based on the demand. Of course, it should be secure, which you see here also, right? So, and all of this security, providing it in a very simple fashion, making it scalable up and down, having good network with subnets well nicely defined so that other users cannot see the others' data and stuff like this. This all is quite some work for a company, and with this a huge effort to actually do that on their own. Now, shortly for multi-core CPU, that has been around. Every laptop is basically equipped with this. You have a typical core. It has several levels of cache and one memory, essentially, right, which is there. So this is something what you know. It was increasingly getting more faster. So that's why it's also getting hotter, unfortunately. And we cannot do these anymore. We cannot put more high single thread performance CPUs on a chip. Instead, what was coming is that moderate performance chips have been put on basically on a GPU to a massive amount degree. They are not that hot, but they really are sufficiently for several parallel tasks to do. And this was a movement that fueled now deep learning, that offered lots of different computing needs. And we review that in the next couple of lectures more in detail while the GPU has done so much work. It came from the gaming industry. So it was also technology that was quite, let's say, well funded. And everybody by now knows NVIDIA, I guess, with all the different GPU component that not only fuel the gaming today, but also lots of supercomputers in the world for science and academics. And at the same time, you can essentially find them in AWS and Google Clouds, in Microsoft Azure. Wherever you go, you can find these resources to buy, of course, for some certain amount of money. Another example of today is the Google Cloud. And I bring this example because students like it typically to think about more practical aspects, how to develop apps. And you see a very famous app that, for instance, takes advantage of the Google Cloud, which is called Angry Birds. So I think in Philips, the sensors, the lights to really steer lights up and down and having data around these. So lots of people, where you perhaps don't know, use inherently or somewhere in the back end these technologies. And the Google Cloud has a very nice platform as a service approach. So there are lots of different services that you can see as Lego bricks, really, right? So you put different Lego pieces together and you have your Angry Birds. You have a billing part of the service, you have a GUI part of the service, you have load balancing, so you can grow with the number of users of your app. I mean, Angry Birds didn't start it with a success. It was a failure, right, in the beginning. A soccer game then came slowly to Angry Birds and then more and more successful. Now you have Angry Birds everywhere. You have lots of different, even movies are done by it, by the way, but now you have lots of different apps around it and they make hell a lot of money. But this took some time to implement. And if you see about the number of users that they have now, right, with 140 million downloads and so on, and users, this needs a scalable infrastructure underneath, something which grows with the demand of the users, which is a key idea of cloud computing, the scalability. And then, of course, parts in this platform as a service idea is really not only have the hardware shared, so GPUs or CPUs, but also some form of a software. A popular example is, for instance, storages, but also billing services, so that you don't want to do this credit card on your own. You have some services that can take care of this already. When you go to the Amazon Web Services, you have another modern software as a service approach, which is then one level higher, where you even don't really touch any metal anymore. You don't really think about specific platforms or programming a lot anymore. You just use different services. And Amazon SageMaker I bring to you as an example because it has direct impact in machine learning. We will talk about this also in lecture 10 much more. But here you have a service in the AWS cloud that, of course, needs to be paid, right? And to a significant degree, because always when you pay the top services like SageMaker, you also have to pay the underlying resources, right? It extracts them away, but you still need computing, you still need storage. And that's why these services, of course, can cost quite something. Here in the course, we get there and here some services, of course, for free. But take away the message that services as those that you can also nicely attach. Here's a Jupyter notebook, very nice to program, similar like we do with MS Azure, that will cost something. And we will review this throughout the course of the lecture. So I think I skip, for the sake of the time, the Cloud Computing Explained video, just again a short remark for this different, you see here the different aspects of SAAS, IAAS, and PAAS. So what is that? If you look this, always think about that infrastructure as a service is really kind of the bottom, right? These are things like the Amazon Web Service having elastic compute services, having a storage cloud where you put some data, and that's pretty basic, right? Also, you can just have a virtual machine, for instance. Then platform as a service sits kind of on top. Of course, it requires CPUs, it requires storage, and so on. But the platform as a service will have already some fundamental services around it. It will have a certain number of functionalities that you can use. For instance, the Angry Birds guys, that they can build on it, that they can quickly build an app around it and just focus on their business logic for the game and don't have to think about it. Oh no, we have to put the user's level data. We have to put this when he is from another coast, geographically dispersed. We don't have a data center there. They just reuse the infrastructure essentially of a cloud provider, as many others do today. GreatScope is another example, is AWS. And then you have SaaS, which really sits on top. Now, software as a service is really things like customer relationship management. We have a whole lecture about it, things you really already know. Lots of platforms on the web, lots of forums on the web, lots of websites are in a SaaS fashion. You go there, you subscribe to something, and then this also has, of course, direct impact to so-called streaming services like Netflix, or where there's also not a real direct cut or boundary, I would say. You will see this in the course, that things from Amazon can be categorized at infrastructure as a service, but at the same time partly platform as a service, because it's quite well advanced. Like we have seen basically a little bit with the Jupyter just now, machine learning, quickly Jupyter. You could say, okay, it's a platform because you have just machine learning, but because you have Jupyter already, you just have to enter some Python code. Some may say it's more a software as a service. So when you see this, don't take it by heart, these different categories. Also take away the message that today you have database as a service, you have design as a service, you have music as a service, you have everything as a service. That's why I meant star IAAS. You will see really when you Google around a little bit, there are lots of these services today around, but they all share in one way or another the idea that everything is a service and you can connect them, you can build on top of them, and they in one way or another should interoperate through the web and through the internet. Right, so much for cloud computing and the foundation. I would like to break here for 10 minutes and then we come back to the second part of the lecture.